Hello everyone, welcome back to the structural equation modeling part of our course. In this part of the lecture, we will talk about the covariance-based SEM. We will study the estimation procedure in this type of the SEM, the model identifiability, the sample size needed to fit the SEM model, and how to assess the model fit and which indices we can use for this. First, let's recall the SEM workflow process. As you remember, we start with the theory, and based on that, we build our hypothesis. And using data, we assess our model with this data. And based on that, we assess model parameters as well as model fit. And the main question which we want to answer with this, whether our data correspond to our model. And on this step of this workflow, we have to get familiar with the model estimation procedures. And in this course, we will study two different paradigms for model estimation. And the first one is called covariance-based estimation. And this is a big part of our course because this is a classic approach to the SEM and has quite a long time of development. And the second estimation procedure is named local equation estimation or piecewise SEM. And this type was proposed not so long time ago, around 2000. We will talk about this estimation procedure, but much more less than about the covariance-based estimation. So the main difference between these two paradigms is that the covariance-based estimation reproduces a single covariance matrix and compares it to the data. And that's why it's named global estimation, because it produces one global matrix. And in contrast to this, the local estimation procedure fit model for each response variable separately and then strings is together the inferences of these models. It's kind like putting puzzle together. And the main package in R for the covariance-based SEM is Lavan, while for the local equation estimation, the piecewise SEM package was developed for biology and ecology studies. And covariance-based estimation is a very powerful tool, but it has some assumptions and which are frequently violated in ecological studies. That's why the local estimation was developed. And now let's dive into the covariance-based SEM. Let's consider that we have three variables in our data set, and then we can calculate the covariance matrix for these variables. And then this covariance matrix is called the observed covariance matrix by our data. Main idea of the covariance-based SEM is to reproduce this covariance matrix using our model structure. And then this reproduced covariance matrix is called implied or model estimated covariance matrix. And then covariance-based SEM takes this model implied covariance matrix and compares to the observed one. That's why the covariance-based SEM can be basically boiled down to this simple equation where the observed covariance matrix S equal to the model implied covariance matrix sigma. But now questions comes how we can come up to this equation and how we can estimate this model implied covariance matrix. And the most common tool is a maximum likelihood estimation, which searches for the minimum difference between these two matrices. As you might remember, the common maximum likelihood fitting function is based on the log likelihood ratio, which compares the likelihood of our model to the likelihood of a saturated model or a model with a perfect fit. And here I show the maximum likelihood fitting function for the SEM. So it basically takes the modeled covariance matrix and compares it to the observed covariance matrix. Also, you can see here included the number of endogenous variables, which are our responses, and number of exogenous variables, which are our predictors. Also, what we have here, the inverse of our matrices, it's denoted by -1 here, and the trace of the matrices, which is the sum of the diagonal. And if the modeled covariance matrix is equal to the observed covariance matrix, then we have the perfect model fit, which yields a value of maximum likelihood function equals 0. And the maximum likelihood estimators are considered as the best estimators because they have a few desirable properties. So principally that they are invariant to the scales of the variables. Also, they provide unbiased parameter estimates. And asymptotically unbiased means that for larger values of sample size, we are going to be closer to the true value. And they are efficient in the sense that no other way of doing this estimation will give us more precise estimates for these parameters. But we should remember that these two assumptions of being asymptotically unbiased and efficient do themselves hinge on some other assumptions, and we will discuss that assumptions in the next lectures. The global estimation procedure in SEM has a few steps, which I would like to show with this slide. And the first step is that we have our hypothesized model structure, and we have the observed covariance matrix from our data. And then maximum likelihood takes these two and calculates the parameter estimates as well as the covariance matrix from our model. And then it takes this model implied matrix and matches it to the observed covariance matrix of our data. And in this way, it tries to find the maximum likelihood between these two. And the estimation computes this maximum likelihood and updates this parameter estimates continuously. And each computation and update is called iteration. So each iteration tries to minimize the difference between these two matrices. And this process goes until the maximum likelihood between them are found. And this step would mean that maximum likelihood has converged. And only on this stage, when it's converged, we can trust to our parameter estimates and to standard errors, as well as we can test our model fit. And the model fit is tested with log likelihood. But in case if maximum likelihood failed to converge, it would mean that our model is not identified. It would mean that there are no enough pieces of information in a model to be able to uniquely estimate our parameters. And this leads us now to the next topic, which is model identifiability. And now the question if we can fit our model is directly linked to the question if our model is identified. And by this, we mean that whether there are enough known pieces of information in a model to produce unique estimates for the unknown parameters. And known information in the SEM are our variances and covariances of our measured variables from our observed data. And unknown parameters are our model parameters that we want to estimate. So this can be our path coefficients or regression coefficients or our variances of the residual errors. To give an example, the first equation here is not identified. And this is because we cannot produce unique estimates for A and B from this equation. So A and B here could really take on many different values, and all of these values would be true in terms of the equation being correct here. And that's why this equation cannot be identified. It means that we cannot arrive with unique estimates. And as we don't have unique estimates for our parameters, then we cannot fit this model. And now let's consider another equation in addition to the first one, which is shown in blue here. So with this equation now, we have enough information to uniquely solve for our B and A here. So we have arrived at a single solution for A and B, and this system of equations which allow to do this are called just identified because we have just enough information to solve for the unknowns. And in order to fit our model, it must be identified. And here is example 3, where in addition to our two first equations, where we already have arrived to the unique solutions for A and B, we add one more equation. And when we have three of these equations now, we have more pieces of known information than unknown information, since we have already calculated solutions for A and B. And such system of equations would be called over-identified, because we have more information than is necessary to arrive at a unique solution for our unknown parameters A and B here. And this is what we need in structural equation model in order to assess the fit of the model. Because when we have just identified models, we can fit the model, but we cannot assess the fit, because in this case we don't have any degrees of freedoms. And in a case of over-identified models, we have positive degrees of freedom, and then we can compare our model to the observed covariance matrix. Here are some examples of model identification status. And you may have heard of models referred to as saturated. Such models would be just identified, and the unsaturated models would be over-identified. And as you might guess, the oversaturated models would be under-identified. And as I have mentioned in a previous slide, to be able to compare our model structure to data, we need the maximum likelihood value. And only in over-identified models, SEM can yield a likelihood value which we can use to assess the model fit. And also what I want to say that when we have such bidirectional links, so we don't know in which actually way information goes, then we might have problem with our model identification, because there are no single solution to parameter estimates. And Lavan would let you know that there might be a problem with your model identification. And here I would like also to introduce new terms, new terminology to the path diagrams, which are non-recursive and recursive models. So if we have these bidirectional feedbacks in our model, then these models are referred to as non-recursive models. And in contrast to that, the recursive models have only causal effects. So all links are unidirectional. But now you might ask whether we can use the non-recursive models in the SEM at all. And we can do this only in specific cases if our response variables in the SEM have unique information, if they have unique estimates, like here shown on this figure. Even if we have the recursive links between our response variables, we still can arrive with the unique solutions for our estimates. And if our model does not allow to produce unique estimates, like here, then it will be not identified. For instance, this additional link here in this model does not allow us to have unique solutions for y1 and y2. What is very helpful in SEM that there is a handy equation which allows quickly to assess the identification status of the model. And you can see the form of this equation here, where S is the number of observed variables. So this is the number of our knowns in the model. Let's consider that we have three observed variables. And here on right, you see the observed covariance matrix associated with our data. And on the left, we have the model which we want to test. Then T maximum here is a maximum number that can be estimated given these three variables. And this can be taken from our observed covariance matrix. So Given three variables, we have maximum 6 parameters that can be estimated from here. And these are variances and covariances among our variables. So T max here equals 6. Then we also have the T rule here, showing us how to assess the identification status of our model. So if our T value equals T max, it's just identified, more than T max, it's unidentified, and less than T max is over-identified. And T here is the number of our unknowns, the number of parameters here in this model that we need to estimate. Have a look on our model and think how many parameters will be estimated from this model structure. Well, of course, we need to estimate two regression coefficients, and these two regression coefficients are actually the covariances among our variables from our observed covariance matrix. But if we recall the previous lecture, then we remember that we need three variances of our variables in order to estimate also these regression coefficients. So from this, we can say that the total number of unknowns here that we need to estimate is equal 5. And now, if we call our T rule, we see that 5, the T is less than 6, than T max here, then our model is over-identified or unsaturated. So if this is unsaturated, then this model can be fitted to the data, and also it would allow us to evaluate model fit and compare model to the data, because we have more known information than unknown information here. And degrees of freedom are equal to the T max minus T, the maximum number of parameters that can be estimated minus the number of parameters that we do estimate in a model. Don't worry about this all. A lot of this information, because you do not need to do these quantifications by hand. When using Lavant, we simply run our model, and the software will warn us if our model is not identified. But it is still very useful to know how to identify the status of the model, because it helps us to understand if our things might be going wrong, if we have a problem and our model is not identified. And the next issue is the assessing sample size for the SEM model. The identification of the model is only the first step in assessing whether we can fit the model. And another important step is to check the sample size. The sample size is important because it can restrict the model fitting by providing not enough replication for our fit function of maximum likelihood to arrive at a stable set of estimates for our path coefficients. So the basic rule of thumb for sample size is given here. So it's equal 5 multiplied per number of path coefficients that we have to estimate. And this is minimum requirement. And for instance, for our previous example, the number of path coefficients is 2 here. And if we want to be more precise, then we can say that we need such a sample size that our K value here of P to the power of 3 divided per 2, and this divided per sample size, is close to 0. So in our previous path model, we are estimating two coefficients. So we require at least 10 replicates to fit the model. However, as I mentioned, this value is a lower limit, and ideally we would need at least 20 multiplied per our path coefficient. But in general, the larger the sample size, the more precise or unbiased would be our estimates. And this is true not only for a structural equation model, but this is true for all linear regressions. So in our case, if we have 40 replicates, then our K value should approach 0. And you can see that it's much lower than in comparison with previous example. And now we can say that both identification and sample size are both very important steps before we know that we can fit our model. And the final topic for today is the assessment of the model fit. In the beginning of the lecture, we have discussed the procedure of the global estimation, which is shown here. And as we have established then, the purpose of the covariance-based SEM is to reproduce the observed covariance matrix from the data, which is shown here by S. But it's not necessary that our hypothesized model would match our data. That's why we have to be ready to test how well the model implied covariance matrix, sigma here, matches our covariance matrix observed by the data. And this is the purpose of testing the goodness of fit of the model. So let's consider our previous example where we have 3 variables in the model. And I suggest that along with the lectures, you reproduce in R the code that I'm showing here. And the data for this example are in Blackboard and they are named CEM data1 txt file. And also you will find here the syntax for the model specified in Lavaan. Also, in addition, I show how to fit the model to our data here. And I want to extract result. For this, I use the function summary, but also I want my results to be standardized. So I use the command standardize equal true. Considering our previous example, we have got the following path coefficients, which are shown here in blue, and they show the relationship between our variables. But if we recall the previous lecture on path coefficients, in addition to that, we also evaluate the error variance or residual variance, which reflects the outside sources of variation, which are not captured by our measured variables. So if we have high error variances of our variables, then we will have less accurate these path coefficients. And this would mean that we have a high level of disagreement between the observed and the model implied covariance matrices. And now let's have a closer look into our model implied covariance matrix, which you can see here. I also highlighted the coefficients in blue as well. So to get this matrix in Lavaan, we can use function law_inspect for our fitted model. And also I want the coefficients to be standardized. That's why I use argument what equals core all, meaning that I want correlations, but not covariations, not the raw scale of our data. And now I would like to compare this our model implied matrix to the observed covariance matrix from the data. And to get this matrix in Lavaan, we can use function law_core for our fitted model. And if we look on these matrices, there seems no differences between them. But there are some differences, and I highlighted them in red here. And as you can see, these differences concern the relationship between x1 and y2. And in our model, you can see that the effect of x1 on y2 is indirect. It's mediated through our variable y1. So, and this indirect effect, as you might remember, is a product of the effects x1 on y1 and y1 on y2. And this effect actually equals 0.49, as I have shown here. And now we want to know how does this effect compares to our observed matrix. And you see some misfit between them. There is some difference. And this difference is actually the residuals, which I have shown here in the previous slide. But to get these residuals, you don't have to calculate them by hand. We can ask Lavan to do this for us. So for this, we can use function resid for our fitted model. And by using argument core here, I ask the residuals in correlational units. And this can be more intuitive than dealing with covariances, the unstandardized units. So here you can see the output, the residual correlation matrix, and the results here, this difference, these residuals here match our residuals calculated by hand. So we can say that this residual correlation matrix is the subtraction of the observed and model implied covariance matrices. And if we would have large negative values of residuals here, this would mean that our model underpredicts the correlation. And large positive values, of course, would suggest that model overpredicts the correlations. And I like to visualize the residuals. For this, I use library ggcoreplot. And here in this library, I use the same function ggcoreplot for our residual matrix, which we obtained here above. And I use here argument co because this argument gives us this matrix. And type equals lower here, it means that I want my variables be specified here in a specific order, x1 first and y1 first. You can use this script to reproduce it in R and try to play with it. So what the script shows us that the differences between our observed and implied covariances or correlations here. And as we can see, these differences are really small here. So this blue quadrant here between x1 and y2 is really low. And yes, it is low because it's 0.05. But this rather small difference, rather small residuals, means that the model underpredicts the association between x1 and y2. But we are not sure what does it mean for our model. Whether should there be a direct link from x1 to y2 here in order to capture this underprediction? And in reality, there are no strict thresholds about how big these residuals can be so that our model is still good enough. And usually values of these residuals here in this correlation, in residual correlation, if they are higher than 0.1, they are worth closer consideration. But this is not a strict rule. And there always be some residuals, and the question is how well then our data agree with the model. And this is what our indices of goodness of fit can tell us, and which we're gonna consider next. And before going into these indices, let's first recall what we know about the maximum likelihood function. As you remember, it compares the modeled covariance matrix to the observed covariance matrix. And if these matrices are not different, if they are totally equal, then we would have the perfect model fit and our maximum likelihood function would be equal to 0. And oppositely, if we would have a large value of maximum likelihood function, this would imply high difference between the observed and the modeled covariances. And this could be interpreted then as a poor fit for the model. In fact, our maximum likelihood function is chi-square distributed, and this allows us to calculate the model fit, which is chi-square here. And this involves our maximum likelihood function and sample size of our data. And now when we get our model fit, our chi-square, we can use this chi-square statistic together with degrees of freedom of the model and compare them to the chi-square distribution. And this will allow us to get the confidence level in our model fit. And as you might remember, the degrees of freedom are determined by the model identification, which we just have discussed in this lecture. So just identified model will have 0 degrees of freedom. And this means that no goodness of fit test is possible for these models. And over-identified models will have some degrees of freedom. And as you remember, we can calculate degrees of freedom using this formula. If you still have questions how to quantify the degrees of freedom, I suggest you to revisit our previous slides on our T rule for the model. And the null hypothesis, which we test with our chi-square statistic, is that there is no difference between the modeled and the observed by data covariance matrices. So when our chi-square equals 0, this means that model fits the data perfectly. And good fit would mean that we fail to reject the null hypothesis. And if we fail to reject it, then our value would be higher than 0.005. And now when we look on our p-value, we should be careful here because the interpretation of this outcome of the significance test is reversed to what we know when we test the significance for the regression parameters. So for good fit, we look on p-values that are higher than 0.005 and not vice versa. And from this also, it follows that larger chi-square would imply lack of fit or poor fit. One more important thing to mention here is that our chi-square is scaled by the sample size. And this would mean that when we have a high number of samples in our data, we cannot use our chi-square statistics as a single measure of goodness of fit. But we have to consider in addition other measures which are not dependent on the sample size. And we will study all these measures later today. And now let's get back to our example. So in Lavaan, as you remember, we have first 3 steps. We specify our model, we fit model using SEM function, and we extract the results. The summary function gives us information about the fit of our model. And let's look first on the header of the output of this function. So first it gives us the version number of Lavaan. Also it informs us that maximum likelihood has converged normally and how many iterations were needed for this. Also, we see here that the estimator that was used is a maximum likelihood, and the optimizer that was used to find the best fitting parameter values for this estimator was this one here. And number of model parameters here is equal 4. This is because we have 2 path coefficients and we have 2 residual variances. Also, we have the information about the sample size, which is 100 rows in the data set. The model test user model is the chi-square statistic, and test statistic is our value of chi-square. And the degrees of freedom here equals 1. This means that we have 1 path omitted from our model. And as you remember, the fact that we have this 1 degree of freedom allows us to test the model fit. And then we also have the p-value of our chi-square. And this, as you remember, is the probability of the data given our model. And in this case, the probability is high. It suggests that our model is consistent with the data and no necessary changes are required. But in case if we have to add some specific changes to our model, then we would need to test the difference between the 2 models. And chi-square statistics allows to do this. We can simply test the difference in the chi-square statistics between the 2 models. And such test is also called chi-square difference. But we can do the chi-square difference test only if we use the same data set and the same sample size. But one more important thing is that we have to use nested models. And by nested models, I mean that one model should be a subset of another model. For instance, model A, a subset of model B. Or another way of saying this is that the nested model is the model with the same variables as the other model, but has some less number of parameters to be estimated. So it has fewer links here. And the model that has less parameters is named reduced model, while the other model with more parameters is named full model. And then, only when we have nested models, we can compare them. However, if we introduce another model here, model C, which has one more additional variable, then this model cannot be compared with chi-square difference test, neither to model B nor to model A here. And this is because they are not nested. And our chi-square difference test is simply the difference between chi-square values between the two nested models. And the degrees of freedom here are the differences in the degrees of freedom between these two models. So our resulting statistic can then be compared to a chi-square distribution, to a chi-square table, which will yield us a new significance value, new p-value. And then we can say whether model A is better than model B or not. For non-nested models, we can use other statistics to compare these models, but we will discuss these statistics in the next lectures. Now we will exercise how to do the chi-square difference test in R. So for this, we will return to our model example, where we were not sure if we need the link from x1 to y2. So we were not sure if our model was good enough. And our chi-square statistics showed us that our model has a good fit and we don't need any changes to the model. But let's say we still want to test this link. So we want to include it in a model and then to test that model to our model, whether it reproduces better fit. For this, in addition to the first model, we have to specify a second model where we add link from x1 to y2. And then we fit this model as well. And similarly, as we do in regression analysis, to perform the chi-square difference test, we have to use function ANOVA, where we compare to our fitted models. And here is output of the ANOVA function, which gives us chi-square difference test. So it gives us the information for model 1 and model 2. So we have here the degrees of freedoms. We have also AAC and BAC criteria informations, but we will discuss them in the next lectures. Important what we have here are chi-square statistics for each model, and then we have chi-square difference between these models and the difference in their degrees of freedom. And then we can use these chi-square differences to compare them to the chi-square distribution, and in this way to test the fit of the model 1 to the model 2. And the significance of this test shows us that there is no big difference if we include the link into our model. This would mean that we would prefer the more parsimonious model. So those models that has less links is simpler and estimating less parameters. So in this way, we can say that we come to the same conclusion that there are no necessary modification needed to our model. Another important issue that we have to keep in mind is that chi-square test is affected by the sample size of the data. So the larger samples we have, more likely is that we will generate poor fit of the model. As an example here, I show the chi-square statistics for the same model, but the different sample sizes. And as you can see here, the lower is sample size, the better is fit of our model. And as soon as our sample size increases, the p-value decreases and we have a poor fit here. That's why, in addition to chi-square, There are other several fit indices for our covariance-based SEM, and these indices, they correct for this problem. In addition to chi-square measure of fit, there are quite a lot of indices which are developed for evaluating model data fit. And to get them, we can ask Lavaan for these indices using the comment fit measures equals true in our summary function. And in addition to chi-square, Lavaan will give us a great deal of information here, and I don't expect you to be able to read all of this. So here you can see a couple of indices, and two of them is a comparative fit index and the Taki-Lewis index. And what they do, they compare our model to the baseline model. And the baseline model is a null model, in which the covariances are fixed to 0. So just individual variances are estimated. If we continue to read through this output table, we will see additional information. So here you can see the IKK information criteria and Bayesian information criteria, as well as the sample size corrected Bayesian information criteria. And we will discuss these measures in the next lecture. But also below is an important measure of fit, is root mean square error approximation. And here you can see the value for this measure and the 90% lower and upper confidence intervals, and also p-value that this root mean square error approximation is higher or equal than 0.05. So this value 0.05 is used as a limit that a good model should not exceed our root mean square error approximation. And so we want this p-value be as close as possible to 1, to 100%. So if we look on this output here, what we can say is that with our estimate of root mean square error approximation equals 0.025, the probability is 36% that this estimate is less than 0.05, and we have a good enough model in this sense. Also below you have the standardized root mean square residuals. And in the next slides, I will show you the table with limits to accept or to reject these fit measures. And actually, Lavaan calculates even more fit indices, which require a different command. For this, you can use the function fit measures to your fitted model. And as you can see here, there are a vast and probably unnecessary number of other fit statistics that have been developed and which you may run across. But again, I don't expect you to read all of this. For now, just to know that since early 1970s, it has been a lot of work done on model fit topics in SEM. And in this course, I will not go into all these possible indices, but I rather will provide you with a practical approach that is sufficient to evaluate model fit for different basic tasks. On this slide, I show the recommended minimum of fit measures that should be shown along with the SEM models. So the first measure, as you might guess, is our model chi-square. And as you remember, the cutoff for the good fit is that our p-value is higher than 0.05. And when we present the chi-square statistics, we should show the chi-square value, the degrees of freedoms, and the p-value for the chi-square. Also, because our chi-square is sensitive to the sample size, we should show our sample size here. The next measure is the root mean square error of approximation, and this is the measures which we have discussed a few slides ago. So this measure is adjusted for the parsimony, for the complexity of our model, as well as it is adjusted to the sample size. And the cutoff for the good fit is generally acceptable when our value is less than 0.1, but it's even more better than when our value is less than 0.08. So when we present this measure, we have to show our RMCEA value, also the 90% confidence intervals, and the p-value that our RMCEA equal or less 0.05. And next measure is our comparative fit index, or S or CFI. So this index also is used because it has low sensitivity to sample size, and the cutoff for good fit is that this index is greater or equal to 0.9. And the last measure here is the standardized root mean square residual. Sometimes if we have high range in the values, like our variables vary in range, then it would sometimes it's hard to interpret the root mean square error. And that's why the standardized root mean square residuals are used. And the same as here, the cut off for good fit is 0.08. And sometimes in ecological literature, you will find some additional measures of the model fit in addition to the previous four indices. And that's why I have shown these measures here. I provide the description for each of these measures and also the thresholds for the good fit. But I will not go into details into each of these measures, and here is the link for the more details if you need. And now when we evaluated the fit of the model and when we have the final results for the model, I would like to show you here the good practice how to present these results. So first I would present the path diagram for the model, and I would specify the path coefficients and their significance. You can use, for instance, stars for p-values to show the significance of the coefficients. Also, it is important to know how much variance for each variable is explained by the model. And this is our R squares for our response variables here. Also, if model have indirect effects, then I think it's important to show them if this is the aim of the study. So for instance, we know here that x1 has indirect effect on y2 through y1, and then our indirect effect is a product of these two coefficients. And the very important part of the results is our fit statistics. And here you see the minimum requirement for our fit statistics. So first we show our chi-square value, the degrees of freedom, the number of samples, and the p-value for the chi-square. Next is our root mean square error approximation, the confidence intervals, lower and upper confidence intervals, and also the p-value, the probability that our RMCEA is equal or lower to 0.05. And we can see here this is probability equals to 36%. And then we have the comparative fit index and the standardized root mean square residuals. And if you compare these measures to the table with the cutoffs for the good fit, you will see that all these measures show the good fit of our model. As you might guess, I reproduced this path diagram by hand here in this PowerPoint, but of course we can use the R to reproduce this path diagram. So for this, we can use the Lavant plot, which we have tried in a previous lecture. So here in Lavant plot, you simply use your fitted model, and also you specify whether you want to present coefficients or not, and whether these coefficients should be standardized or raw. Also, if you want to show the stars for the coefficients, you can use the comment or the argument stars equal regress. And usually these regression coefficients from R have many digits. That's why we can limit these digits to some specific number. Here is the summary on this topic on the goodness of fit in the SEM. So when we assess the overall model fit, we ask whether our model adequately represents the data and also whether we miss any important links in the model. And when we miss important links, our parameter estimates might be not correct and our model might be misspecified. In the next lectures, we will talk about how to search for the missing links, even though we have already touched on this topic, but we will discuss this further in the next lecture. And now it's a time for your task. This is the final task for today, for which we will use the data of Grace and Kelly. And in this study, they looked at post-fire vegetation recovery in southeastern Californian woodlands. For this, after burns, after fires, they established 90 plots, and on each plot they examined the woody remains. Here you can see the photo. And when they examined these woody remains, they estimated the age of the stands that burned and also the sensitivity to the fire. So the variables are named age and fire sieve respectively here. Also, in addition, they measured the vegetation cover, named by variable cover here. And the data set can be found in package piecewise SEM, and data name is Kelly. The key observation of the study was the negative relationship between the age of stands before they burned and the cover of vegetation after the fire. But the author, John Kelly, he suggested that older stands would have more fuel and as a result they would burn hotter. So they would have greater fire severity. And more severe fires in turn could explain the reduced recovery in older stands. So the idea was that age should affect the recovered cover, not only directly but also indirectly through the fire severity. And here are your tasks for this exercise. So for the model 1, which is shown on a figure 1 here, you need to check what is the model identifiability status. So where the model is identified, under-identified, or over-identified, and also based on that whether it is saturated or unsaturated, and whether model is recursive or non-recursive. Next, you need to assess the sample size, whether it is enough to fit this model. And for this, you need to use data Kelly from the package piecewise SEM, as I have shown in the previous slides. And third, you need to fit the model in Lavaan and get the path coefficients for each of this relationship here. Also, in addition, you need to get the fit indices and assess the goodness of fit of this model. And the final task here is to test if the link from age to cover, as shown on figure 2 here, is missing in this model. So for this, you need to specify the model 2 as well in Lavaan, and then to use the chi-square difference test, or it's also known as a likelihood ratio test, to compare these two models. Good luck with this model. This was the last topic for today, and looking forward to see you all on the seminar.